Hi, I'm Bruce Torrence, and I want to talk today about one of my favorite aspects of mathematics, and that's how stunning complexity can arise from very simple ideas. And this image here, for example, looks impossibly complex. It's actually made up from just a few squares, and I want to show you how. Here's a slightly simpler example of the same phenomenon. How many squares do you see there? We can all see 7 around the outside. Can you see those toward the center? They're the same size as the ones on the outside. Let's tease this apart and see if we can get at what's going on. The concept I want to explain is called the symmetric difference. And we've all, it's very easily illustrated in terms of a Venn diagram, and that's what we're looking at here. If you have 2 disks, you can overlap them like so. And we're all familiar with Venn diagrams. This little portion in the middle is called the intersection of the 2. And the entire conglomeration is their union. What you're seeing here with these top 2 disks is their symmetric difference. It's technically the union minus the intersection. And if I were to take the symmetric difference of this object with, say, a 3rd disk, it looks like this. Essentially, all the subregions that are enclosed in an odd number of the disks are included in the symmetric difference. And all those subregions that are only in an even collection of the disks are not included. It's a remarkably simple idea. If you were to just see this picture, though, and be told, well, that's 4 disks. I mean, it's made from 4 disks. You might be a little surprised. It might take a moment before you can really see the individual disks. And that's what's going on here. We can highlight the symmetry of the operation by using a computer to place those disks very precisely. I'm just changing their radius here and looking at what the symmetric difference looks like. If there were 5 disks, we'd get something like this, or 6, we'd get something like that. You get these beautiful pictures from symmetric differences. And only in the past 20 years ago has computing machinery gotten really good at rendering symmetric differences of geometric objects, things like disks and triangles and squares, really, really quickly and really, really well. So I'm going to take advantage of that and play with some things. Let's take, for example, 4 triangles. I'm going to take this triangle that's outlined and rotate it about this point here and get 4 other copies. And they don't overlap at all. But with this little interactive figure, I can actually move the center. And what I'm looking at is the symmetric difference. The overlaps are removed. If there were 5 of them, each one obtained from the other by rotating through 72 degrees, 1/5 of the way around, we get something like this. With 6, you get something like that. You can get really complicated figures by taking a simple shape and just rotating it around some central point. And that's how those original figures were made. And anybody can do this with a little bit of software. And here's, for instance, how those original figures were made. I start with this parametric curve. Let's call it a rosette. It's got 7 lobes on it, 7 little curlicues that stick out like flowers, petals on a flower. So what I'm going to do is take a square and draw a line through its one of its diagonals and place the center of the square right on that curve. And then I'm going to go around the curve part way and place another square. And then take the symmetric difference of the 2. And then go around the curve a little more and place a 3rd square. I've got 1, 2, 3 squares. The 4th square is going to go on the tip of the 2nd lobe. I'm going to do essentially 3 squares per lobe all the way around. So there's number 4, 5, 6, 7. I'm taking symmetric differences as I go. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 21. 7 times 3 is 21. 7 lobes, 3 squares per lobe, 21 different squares. So in blue, we're looking at the symmetric difference. If we were to remove all that construction apparatus and just look at the resulting pattern, it looks like this. And that's one of the patterns I showed you right at the beginning with the 7 squares along the outside. But in the middle, these are the other squares. It's because of the symmetric difference most of them have been, most of those squares are not present in the final image. We could do 4 squares per lobe and we'd see something like this. 5 squares per lobe would look like that. We could change the size of the squares so they get bigger. And impossibly complex patterns emerge. And that was the, this is how we saw that. This is what that first figure was at the very beginning of this very brief presentation. So my point is simply that simple rules can yield beautiful complexity. And here in the 21st century, we have such a wonderful opportunity to explore these things with the computing machinery available to us. So I encourage all of you to get out there and find a very simple computer program to make symmetric differences of shapes, arrange them any way you like, and marvel at the patterns. Thank you, and stay safe.